Now I can apply a direct potential field with all these values. But then what I'll do is that if I directly apply a potential field, I might get exactly the same problem as a potential field, which is that it doesn't go into narrow corridors, and exactly the same thing will happen here. I've avoided the infinity. However, it doesn't mean that problem is solved. So I'll just try to add a tinge of geometry over here. So I'll try to add geometry over here. And when I say I'll try to add a geometry over here, so let us try to foresee some kind of a geometry in this. And if I need to foresee some kind of a geometry into this, let me make in what is the polar obstacle density. And when I say polar obstacle density, I mean to say that the data is into 2D. I'm bad at 2D as it's already known, so I'll try to convert this into something which is one-dimensional. And the best way to convert any dimensional quantity into one-dimensional is by doing a histogramming. So here the histogramming converts 2D to 1D. So what I'll do is, I'll take in buckets of angles. So let's say 0 to 30 degrees, 30 to 60 degrees, 60 to 90 degrees, and all the way up to 330 to 360 degrees. And what I'll do is I'll put in all the obstacles that lie in this radial range. I'll put all the obstacles that lie in this radial range. I'll put all the obstacles that lie in this radial range. I'll put all the obstacles that lie in this radial range. And it'll not be a count of obstacles 1, 2, 3, 4, 5. It will be weighted by the importance of the obstacle. So I will add in a FO magnitude in the correct bin, and I'll take the magnitude of the total forces of the obstacles that lie in that bin. So angles in which there are a lot of obstacles will have very high magnitude of obstacle density. Angles which are free, no obstacle, will not get anything added into M. Those buckets will be empty. Places where the obstacles are large in number but they are far off will be completely free. They are obstacles but they are not important, they are far off. Places which have very few obstacles but they are very close by will be full. Only few obstacles but those matter because they are nearby. So I'm going to do this histogramming technique, and this histogramming is let any one of those histograms be HI, so the histogram of I, and histograms have, I don't want to take, the normal range is minus pi to pi. I don't want to go minus pi to pi. I want to go 0 to 360 degrees. So this is minus pi to pi. So let's make it 0 to 2 pi. So I consider the obstacle XOYO, and in this XOYO, what I do is theta O is equal to a tan 2 YO minus YR XO minus XR. I need to decide which bin does it belong to. So it belongs to the bin, the ith bin has an angular range similar to this. So that's inclusive, that's exclusive. It's the same. So alpha is the resolution. So here I had divided into 360 divided by 30, 12 bins. So in general, I divide it into alpha bins. So I find out this, where does it belong to? So let's say this was 75 degrees. So does 75 come in this range? No. This range? No. This range? Yes. So I'll put F0 over here. So let's total all the things which get inside the ith bin. So HI, all the things which get inside the ith bin is given by a submission over all XO, a submission over all YO, FO, which is XOYO, such that the angular range is satisfied. I minus 1 2 pi by alpha is less than equal to theta O is less than equal to I into 2 pi by alpha. And of course, x0 is from xr minus w by 2 to xr plus w by 2. It's a w cross w window, and similarly for y0. yr minus w by 2 to yr plus w by 2. So this one is the total obstacle density around. I won't be able to plot it up, but let's see what happens. So at minus 20 degree, which is approximately 340 degree, I have obstacles. So around, so that's 360 degree. So 360 degree there is nothing. Then across 340 there is something. So that's obstacle density. Here also there are too many obstacles, but they are far away around 60 degrees. So that's around 60 degrees. So this is around 340, this is around 60. And similarly here at around 180 degree, there are quite a few obstacles, but they are all small. So this one obstacle density is actually small. So 180 will be right here. There's another small, and this one extends for quite many degrees. So that's obstacle density. When I apply histogramming to it, the only thing that changes is the histogram are given by, so nothing, nothing, nothing. I think a bigger one over here and around 180 degree, some over here, and then there's a peak around 340 degree over here. So if they are far off, the effect will be smaller. If they are larger in number, the effect will be larger. If they are nearer, the effect will be larger. If they are smaller in number, the effect will be smaller. That's what I plotted as HI. So that's H1, H2, H3, H4, and so on. So that's the polar obstacle density that is plotted around over here. That's HI. Now, one thing which obviously happens is that the moment you do all these calculations, here what happened was that there was a threshold. So 0 to 30 degree here, 30 to 60 degree here, and sometimes the angle, these thresholds can be very funny. So you say at 30 degree there's a big obstacle, but then it disappears at 31 degree. So the robot says that okay, at 31 there's nothing, and it tries to go at 31, but then 30 there's an obstacle. So the moment you've got such hard limiting factors, computationally it becomes extremely difficult, it becomes a hell. So that's why you incorporate some fuzziness, that 31 shouldn't be very different from 30, shouldn't be very different from 29. Luckily 29 and 30 degree are in the same bin over here, so they have to be exactly the same, but 31 can be is a different bin, so it suddenly has a very different value. And these hard thresholds give in a big time. imagine writing down a program, if condition, then this, else this. Now, at the boundary condition, the behavior suddenly changes. So from obstacle avoidance, your robot starts doing goal seeking. From going away from the obstacle, it starts going towards the obstacle. The behavior suddenly changes, and those sudden changes are bad. So what we're going to do is we're going to do some fuzzification, some smoothing, so that the effect of hard thresholds is smoothened around. So we're going to do smoothing, and the smoothing is going to be done by moving average. Now remember, whenever I plot things like this, now 0 and 360 degree are exactly the same thing. So more correctly, the obstacle density was like this. It is continuous 0 to 360 degrees, so that's 0 and that's also 360 degree. But I cannot plot this thing up, so I split it across over here and I plotted it as a straight line, which is over here. It doesn't mean it's non-circular, and I'm gonna take care of that when I apply moving average, that the angles are circular. So let's take in random numbers: 5, 15, 23, 86, 29, 45, and 33. And let's apply in moving average. So this is the smoothened one. Now I'm not going to do the mathematics, but I'm going to apply moving average of size 3. So this will become 5 plus 15 plus 23 divided by 3. This is gonna become 15 plus 23 plus 86 divided by 3. This is gonna become 23 plus 86 plus 29 divided by 3, and similarly moving average of 3. So take the left one, take the right one, take the number itself divided by 3. 86 plus 29 plus 45 divided by 3. 45 left right, 29 plus 45 plus 33 divided by 3. 33 1 left, 45 the number itself, 33 1 right. What comes after 33? It's circular, angles are circular, plus 5. 5 what comes on the left, angles are circular, 33. What comes on the right? 15 divided by 3. So it's a moving continuous average of window size 2w by 1, or w is already used, so let us say of size 2k plus 1. So k numbers on the left, k numbers on the right, one number at the center of size 2k plus 1. In this example, k was equal to 1, so it was a window size of 3. Or in general, I say hi dash, so hi dash, where dash means smoothened, is equal to hi plus j, summation j is equal to minus w to w. Now I need to say circular, so I need to say a mod of the total number of bins. How many bins are there? Alpha. Now this can become negative, as this was becoming minus 1. I mean, it was becoming minus 1, so I'll have to add a plus alpha over here. That's modular arithmetic, and divide by 2k, 2k plus 1 minus k, 2k. So that is my smoothened histogram. So all that I know is, number one, I know the polar obstacle density, which is this. Then I know the obstacle density in terms of a histogram. So I had some information loss over here, and then I apply some kind of a smoothing. So I apply some kind of a smoothing. So this was smoothing and this was histogramming. So after this, I basically have an idea about what is my histogram gonna look like. It's gonna look like this. Smoothened version. Now what I do is I have another information loss. So at every step I will incur an information loss so that I can make my decision. So what we're gonna do is we're gonna have another information loss over here, and that's called as binarization. So in binarization, what I say is, I say something is there's an obstacle at an angle or there's no obstacle at an angle. I don't say more obstacles, less obstacles, too many obstacles, few obstacles, some obstacles. I say obstacle or non-obstacle. I binarize it up. So I say HI binarize is equal to either 0 or 1, either no obstacle or an obstacle. It's an obstacle if it's greater than a threshold, if it's less than a threshold. So we binarize it up. And that's exactly what I'm going to just show it in this cartoon. And we say that's my threshold. So anything above this threshold is obstacle 1, anything below is not an obstacle 1. So it's binarization. No obstacle, no obstacle, no obstacle, and then suddenly there are 3 obstacles. So now it's not big obstacle, small obstacle, it's either obstacle or non-obstacle. No obstacle, so 180 degree we saw that the obstacles were too far away. So here the obstacles were too far away, so they got eliminated. Here also the obstacles were far away, but there were too many of them, so the cumulative effect was large. And now slowly you can start seeing a geometry. So you can say that around 60 degree over here and around 340 degree over here, there are obstacles. And it's all 0 or 1, so it's either that there is an obstacle or there is no obstacle. There is no intermediate case. So now what? So if you look at it, I get an interesting geometry over here where these are called as the valleys and these are the hills of equal sides. So of course I'll go in a direction where there is no obstacle. There may be an obstacle far away, but as for density there is no obstacle. So I'll go in a region such that it's obstacle free. I'll go in those type of regions where they are obstacle free. So let's first summarize that we had a polar obstacle density that's continuous. Then we had a polar obstacle density histograms, HI. We smoothed it up, HI smooth, and we created them as hills and valley, binarized.